In the northwest corner of Saudi Arabia, there is a trench in the desert. It is not a small trench. It stretches for kilometers across one of the most isolated and hostile landscapes on the planet. And that trench is the beginning of what the Saudi government has described as the most ambitious construction project in the history of human civilization. They call it the Line, 200 kilometers long, 170 meters wide, 500 meters tall. A fully enclosed, climate-controlled, mirrored megastructure designed to house 9 million people. No roads, no cars, no ground-level streets, no sprawl. Just a single, linear, vertical city, cutting across mountains, desert, and coastline, powered entirely by renewable energy. The promotional material is extraordinary. It looks like something from a science fiction film set several centuries from now, and that is precisely the problem. Because behind the renders, behind the announcements, behind the scale of ambition, there is a set of engineering realities that the press releases do not cover. This is not a video about whether the Line is a good idea. This is a video about whether it is a buildable one. This is Next Build, where we break down the world's most ambitious engineering projects. Let us start with scale, because the scale of the Line is not something that translates well from a screen. You have to build a mental model of what 200 kilometers actually means as a structure. 200 kilometers is the distance from London to Birmingham. It is longer than the distance from Los Angeles to San Diego. Laid across a map of France, it would stretch from Paris almost to the Belgian border. Now imagine that entire distance is not a road or a rail line. Imagine it is a single enclosed building, a building 500 meters tall, which makes it taller than One World Trade Center in New York, a building 170 meters wide, roughly the width of a standard city block, and a building that runs without interruption for 200 kilometers. The floor area contained within that structure, if you stack it across all levels, runs into the hundreds of millions of square meters. For reference, the largest building on Earth by floor area right now is the Chengdu New Century Global Center in China. Its total floor area is approximately 1.7 million square meters. The Line, at the population densities proposed, would need to contain something in the range of 40 to 50 times that, in one continuous structure. That number is worth sitting with for a moment, because it is not a building. It is closer in scale to building a small country, and then putting a roof on it. Here is the thing about mega projects that the announcement never tells you. Every large-scale construction project in history has a gap between what was proposed and what was delivered. The Sydney Opera House was budgeted at $7 million and cost $102 million. The Channel Tunnel came in at 80% over its projected cost. The Boston Big Dig, a highway rerouting project, was budgeted at $2.5 billion and ended up costing nearly $15 billion. The Line is not a highway rerouting project. It is an order of magnitude more complex than any of those. And it is being built in a desert with no existing infrastructure, no fresh water supply, and summer temperatures that regularly exceed 45 degrees Celsius. The gap between announcement and delivery here is not going to be small. The question is how large it actually is. To understand why this is so hard, you have to understand what it takes to build at this scale in this location. The Tabuk region of Saudi Arabia, where the Line is sited, is not a construction-ready environment. There are no deep-water ports nearby capable of handling the volume of materials this project requires. The road network in the region was not built for the kind of industrial supply chain you would need for a project of this size. That means the logistics infrastructure has to be built first. Before a single floor of the Line goes up, you need roads capable of carrying heavy freight across hundreds of kilometers of terrain. You need worker accommodation for a labor force that analysts estimate would need to peak somewhere in the range of hundreds of thousands of people on site at once. You need fuel supply, food supply, water supply, all of it, in a region that currently has very little of any of those things at scale. The construction of the Line, in other words, requires building a second city first, a temporary city with all the infrastructure of a permanent one, just to support the workforce. And the concrete alone tells a story. A structure of the Line's proposed dimensions, built to a standard that could support the loads involved, would require hundreds of millions of cubic meters of concrete and structural steel. Concrete needs water to cure. In the Arabian Desert, water is not a freely available resource. Every liter of water used in construction either has to be transported in or extracted from desalination, which itself requires energy and infrastructure. None of these problems are insurmountable, but none of them are free, and none of them have been publicly accounted for in the headline cost figures. There is a concept in engineering called the critical path. It is the sequence of tasks where any delay in one step delays the entire project. On a normal construction site, you manage one critical path. On the line, you are managing critical paths across 200 kilometers of simultaneous construction. A delay in the delivery of structural components at kilometer 40 does not just affect kilometer 40. It can cascade back through the entire logistics chain. When you multiply that problem across dozens of simultaneous construction fronts, in extreme heat, in a remote location, with a workforce that has to be housed and sustained on site, you begin to understand why the timeline was always going to be the hardest engineering challenge of all. Now, let us go inside. Because the construction challenge, as large as it is, may actually be the easier half of this problem. The harder half is what happens when people start living there. Start with the atmosphere. The line is not a collection of buildings connected by outdoor streets. It is a single enclosed volume. Every cubic meter of air inside it has to be mechanically managed. Temperature, humidity, air quality, CO2 levels, particulate matter, all of it continuously across the entire 200-kilometer length. Standard commercial HVAC design operates at the level of individual floors or at most individual buildings. The engineering of a climate system for a sealed structure of this volume has essentially no precedent. The closest comparable environments are things like underground mines, submarine bases, and sealed research stations in Antarctica. None of those house 9 million people. None of them have a 200-kilometer corridor to manage. And crucially, none of them are located in a climate where the outside temperature is hot enough to cause rapid death if the system fails. That last point matters more than it might seem. In a conventional city, if the power goes out in summer, it is dangerous. In the line, if the atmospheric management systems fail, it is catastrophic within hours. That means the redundancy requirements for every climate system in this building are not standard commercial grade. They are closer to life support grade. And designing, building, and maintaining life support grade redundancy across 200 kilometers of enclosed structure is a cost and engineering burden that does not appear anywhere in the headline numbers. Then there is water. 9 million people require enormous quantities of fresh water every day. The Tabuk region has no meaningful surface water supply. That means the line would be entirely dependent on desalination, likely from the Red Sea coastline where the structure meets the water. Desalination at the scale required to supply 9 million people is an industrial operation in its own right. It requires vast energy inputs. It produces brine as a byproduct, which has to be managed carefully to avoid environmental damage to coastal ecosystems. And it creates a single point of vulnerability in the city's water supply chain. If the desalination infrastructure is disrupted by equipment failure, by extreme weather, by any number of other factors, there is no backup. You cannot drill a groundwater well sufficient to supply 9 million people on short notice. Resilience in water supply for a city of this size in this location requires either massive storage capacity, which takes up space and structural volume that has to be accounted for, or redundant desalination systems, which multiply the cost and energy demand further. Now let us talk about movement. NEOM's published concept for the line includes a high-speed underground transit system running the full length of the structure. The stated journey time from one end to the other is 20 minutes. If you do the simple division, 200 kilometers in 20 minutes, the implied average speed is approximately 600 kilometers per hour. That is the speed of a commercial aeroplane at cruising altitude. The fastest maglev technology currently in operational testing in Japan reaches approximately 600 kilometers per hour under ideal conditions. It does this in open, straight, purpose-built test tracks, not inside the basement of an inhabited building 500 meters above it. Running a transit system at those speeds through an enclosed structural corridor raises questions that have never been solved at this scale. The pressure wave generated by a vehicle moving at 600 kilometers per hour in a tunnel is significant. Managing that pressure so it does not create a destructive shockwave requires careful aerodynamic engineering of the tunnel geometry. Stopping distance at that speed, in an emergency, requires either extraordinary braking technology or a stopping zone several kilometers long. Emergency evacuation from a train traveling at that speed inside an enclosed structure in the middle of a desert requires protocols that simply do not exist yet. And remember, in the line, there are no roads, there are no cars. There is no surface street to flag down a taxi. The transit system is not one option among several. It is the only option. If it goes down for scheduled maintenance, the entire city's ability to move is compromised. If it goes down unexpectedly, the consequences scale with the population. At 9 million people, a transit failure in the line is not an inconvenience. It is a public safety emergency. Which brings us to cost. And here the numbers become genuinely difficult to pin down, not because of secrecy, but because the scale of the project makes accurate estimation extremely hard. NEOM's initial public figures suggested a total project cost in the range of $500 billion. Independent analysts, working from the structural requirements and logistical complexity, have placed credible estimates significantly higher. Some analyses have suggested the full cost, accounting for all infrastructure, transit, water, energy, atmospheric systems, structural engineering, could approach or exceed $1 trillion. To put that in perspective, $1 trillion is roughly the entire annual GDP of the Netherlands. It is more than the United States spends on its entire federal discretionary budget in a year. It is an amount of money that, even for a sovereign wealth fund as large as Saudi Arabia's, represents a generational commitment of capital. And by 2024, the internal targets for the project appear to have shifted substantially. Reporting from sources inside the project suggested the population goal for the initial phase had been revised from 9 million, down to somewhere in the range of 300,000 residents. That is a reduction of more than 96%. A city of 300,000 is a real city. It is a meaningful project. But it is not the line as it was announced to the world. The gap between 300,000 and 9 million people is not a rounding error. It is the difference between a demonstration project and a new model for human civilization. And the fact that the internal numbers moved that far, that fast, tells you something about the distance between the ambition of the announcement and the reality of the engineering. None of this means the project is worthless. Real ground has been broken. Real infrastructure is being built. The site exists. Money has been committed and spent. And some of the ideas embedded in the line, the rethinking of urban density, the separation of pedestrian and transit layers, the integration of nature into vertical space, are genuinely interesting concepts that urban designers and engineers will be studying for decades, regardless of how the project unfolds. But interesting concepts and buildable cities are two different things. The history of architecture is full of visionary proposals that produced extraordinary ideas and deeply compromised buildings. The Pruitt-Ego housing complex in St. Louis was celebrated as a triumph of modern urban design. It was demolished 20 years after it opened. Scale does not validate a concept. Execution does. And execution at the scale of the line, in the location of the line, at the timeline of the line, requires solving a set of overlapping engineering problems that have no precedent. The atmosphere problem, the water problem, the transit problem, the construction logistics problem, the redundancy problem, the cost problem. Each one of those, individually, would be a serious engineering challenge for any project. The line has to solve all of them simultaneously, in a desert, at 500 meters of altitude, across 200 kilometers. That is not a reason to say it cannot be done. It is a reason to ask, carefully and seriously, what version of it actually can. Scale is not a vision problem. Scale is an engineering problem, and engineering, in the end, does not negotiate with announcements. If you want more breakdowns like this, projects where the engineering reality is more interesting than the press release, subscribe to Next Build. New videos every week.